Okay, got it. All right, thanks for the reminder, Joe. Appreciate it. All right, so having one server is obviously not ideal. So let's do something slightly more complicated and have multiple servers. Rather than having one copy of the key value store, let's have, for example, 3. So now we're going to have 3 servers, all of which will have all the keys. And again, we'll have our 3 clients. And now a client, in order to send a request, it can't send it to just one of the servers. It has to send it to all of them. So let's say this client says, I'd like to set X to 1. It's going to send it to all 3 of the servers. They'll all get it and they'll all say, yeah, no problem. They'll set X to 1. And they'll reply back. And the good thing about having multiple servers is that now if one of these servers fails, let's say the bottom server, no problem. I don't care. I have 2 other copies of this exact same data. I don't mind if this server fails. Of course, that only works to a point. If every machine fails, it doesn't really matter how smart your distributed system is. At that point, you're kind of out of luck no matter what. So to make the problem tractable, we're going to assume throughout the talk that we have at most F failures for some parameter F. So I'll be assuming that pretty much throughout the entire talk. Okay, so this naively seems like a good idea. We just have multiple copies, send to everybody. If something fails, it's no big deal. But unfortunately, this naive approach also is not quite correct. And the reason is that we can have the following situation. Let's say that 2 clients both send requests at the exact same time. So let's say client 2 says, hey, I'd like to set Y to 2. And this bottom client says, well, I'd like to set Y to 3.
Excuse me, yeah. Question. I see your drawing. Is the camera supposed to be on what you're drawing or in your face? Sorry, bad.
No, you should be able to see my screen. Thanks for pointing that out.
I can.
No worries.
Screen sharing looks fine.
Okay. Yeah, you might.
But is it possible, Adam, that you have him pinned or something?
Yeah, I think it's on my side. Sorry about that.
No worries. No, thanks for interrupting. I appreciate it. I definitely, if anybody has any problems, feel free to jump in. You might have to toggle with like the settings at the top or something. All right, so the reason that this leads to some trouble is because messages sent over the network, we have no guarantee about exactly the order in which they're going to arrive. So we can have something happen like this, where the top server receives the red message first and sets Y to 3, and then it receives the green message and sets Y to 2. The second server, though, might receive the green one first and then the red one. And if it does this, we get in this situation where the 2 servers disagree on what the value of Y should be. The top one thinks it should be 2, the middle one thinks it should be 3. And that's not good. That's not what we want. We're supposed to have multiple copies of the same data. We don't want every replica to have different copies of the data. That's not what we want. Okay, so this is not good. So how do we avoid this? Well, we can use something called state machine replication. This is a super old technique and it's pretty much what my entire thesis is on. State machine replication. So I'll introduce state machine replication first at a very high level before we dive into it a little bit deeper. So let's say we have a black box that is called state machine replication. And for now, I'm going to keep the details hidden away. But I'll label this black box multi-Paxos, which is a state machine replication protocol. So we're going to have our replicas as before, except in the abstract, in the most general sense, instead of just being key value stores, we're going to have multiple replicas or multiple copies of some state machine. And that's just a fancy way of saying some system which has state that can service requests. So you can think of them as key value stores or databases, whatever you want. You can model most things as a state machine. And we're going to have our clients as before. And now what's going to happen is when a client wants to suggest a command, wants to run a command, it's going to send it not to the replicas, but instead to this state machine replication protocol, which for right now is just a black box. So the first client maybe says the set X to 1, the second client sends the set Y to 2, and the third client sends the set Y to 3. And the whole point of a state machine replication protocol, its one goal, its one and only goal, is to order these commands into some log, some totally ordered log. So here's the log. And the state machine replication protocol is just going to put them in order and then make sure that all the replicas execute those commands in the exact same order. So maybe this protocol multi-Paxos says, okay, I think set Y to 2 should be first and then it's going to send set y to 2 to the replicas and make sure they execute it. Then maybe it'll say, okay, next up, let's do set x to 1. It'll send that to the replicas. And then maybe it finishes off and says, okay, maybe we should set y to 3. And the point is that if I have multiple copies of a state machine and they're all executing the same commands in the exact same order, and they're starting in the exact same state, they're always going to be in sync. They're always going to be perfect copies of one another. And we're not going to run into that problem in the previous example where different copies become out of sync. Any questions so far on this? Okay, perfect. So this is the goal of state machine replication at a high level. This is how all state machine replication protocols work. Now let's peer into the black box that I'm calling multi-Paxos and understand how this protocol works at a more concrete level. So multi-Paxos. Thankfully for this talk, I won't have to explain the entire protocol in full. Understanding the entire thing will take more than a 50-minute talk. But at a high level, a multi-Paxos deployment looks something like this. We're going to have our clients, as always. We're going to have a set of machines, a set of servers, which are called proposers. And one of these proposers, I'm going to elect as a leader. So I'll draw it with a crown. We're going to have some number of machines called acceptors. And we're going to have our replicas, as always. We always have replicas. Now, when a client wants to run some state machine command, like set x to 1, it's going to send the command to the leader. Let's say this command is x. The leader is then going to put this command into a log. Remember, that's the whole point, is to make a log. So the leader's responsibility is it's going to start serializing or sequencing commands into a log. So maybe this leader says, okay, command x, that'll go in the first log entry. Then the leader is going to perform a round trip of communication with a majority of the acceptors. The details of what these messages are, I'm not going to get into. You won't have to understand that for the rest of the talk. Just understanding sort of the high level flow of messages is good enough. But trust me when I say that the leader has to perform a round trip of communication with the majority of the acceptors. And majority here is important, and that's going to come up later. So let me write that down, majority. So I drew 3 acceptors here, so the leader has to talk to 2 out of the 3. Then the leader will let the replicas know that this command x was chosen in the first log entry. The replicas will all have their own little copies of the log. They'll put x in the log, and they'll be executing commands, like I said earlier, in log order. So they'll execute x, and then one of the replicas will return the result of executing x back to the client. Any questions on that, at least at the sort of high level flow of the protocol? Client to leader, leader to acceptors, leader to replicas, and one of them responds. Okay, cool. So if you pick up any paper on state machine replication, I'd say like half the time the paper is going to mention that multi-Paxos is too slow. That's a very common thing that people say. Multi-Paxos is too slow. And you might think, okay, what do we do when protocols are slow? We try to scale them up. And there's sort of this misconception out there that multi-Paxos doesn't scale. It's not, people don't really think of scalability when they think about consensus or state machine replication. That's not true. The whole point of sort of my thesis is to show that that's not actually true. But before I dive into how we can scale multi-Paxos up, I want to take some time to sort of explain why people think it doesn't scale. So let's look at these misconceptions. Multi-Paxos doesn't scale. It's not true, but I think it's helpful to understand sort of where people are at when they sort of say this. So multi-Paxos.
I just want to inject a point of sympathy, which is that the first time I built a Paxos at Google, there was a lot of, it will never work, it won't scale. Jeff and Sanjay thought we were crazy. And we had to just kind of quietly go off and do it in the corner and let it run at scale for event and let people get hooked on consensus for eventually people to be like, you know what, maybe papers are wrong or they get the wrong assumptions or something. Mm-hmm. So I love that you're trying to tease that apart, and I hope people start reading those papers.
Yeah, thanks, Alex. And it's super good to get perspective from industry and someone who's had time in the trenches actually doing this stuff. So yeah, I definitely think this is a very widespread sort of view of Paxos. Okay, so multi-Paxos consists of 3 main components. There's the proposers, there's the acceptors, and there's the replicas. So let's go through each one by one, and try to see what happens when we try to scale them up. We're going to see maybe it doesn't quite work. So first up, the proposers. All right, so I'm going to draw the protocol with the clients, as always. I'm going to have the acceptors. I'm going to have the replicas. And now let's see what happens if I have more proposers. So instead of drawing 2, let me draw maybe 5. 1, 2, 3, 4, 5. And as before, I still need to elect one as the leader. And the reason for that is I want a single node doing the sequencing. If I have multiple nodes all trying to organize the commands into a log, it gets messy. That is possible for sure. There are protocols that do that, but it gets messy. So for Paxos, we need a single leader. And then let's execute the protocol. We go client to proposer, proposer to acceptors as before, leader to the replicas, and one of the replicas back to the clients. And we see that the protocol, it doesn't really change at all. Adding more proposers doesn't really do anything because all these other proposers, they're not doing anything. And why is that? Well, the only point of a proposer that's not a leader in normal multi-Paxos is to take over if the leader fails. But in the normal case, when the leader hasn't failed and it's just sort of doing its thing, the proposers are just sort of sitting there doing nothing. So if we add more, the performance isn't really going to change. So this has no effect. You can add more if you like, but it's not really going to do anything. Okay, so that was proposers. What about acceptors? Let's try to add more acceptors. So I'll draw the clients, I'll draw the 2 proposers, and I'll have our 2 replicas. But now let's have, and let me draw the crown. Now let's have more acceptors. Let's draw maybe 7 acceptors. 1, 2, 3, 4, 5, 6, 7. So instead of 3, I'll draw 7. And let's do the protocol. So we go client to leader. And now the leader, like I said before, has to talk to a majority. So that'll be 4. So I'll go 1, 2, 3, 4 acceptors. They'll all respond. And then the leader will let the replicas know. And one of the replicas will respond to the client. So this has just made the protocol worse. Now I'm just sending more messages. It certainly can't make things go faster. I'm doing everything I used to be doing, except now I'm doing more. I'm sending more messages. I'm not doing anything less. So this can only make the protocol slower. So this just hurts performance. And in fact, there's quotes from papers which says something along the lines of using more than 2f+1 acceptors is possible but illogical, something, something, something. So people don't think that you should add more acceptors. In fact, they think that you should use the bare minimum number of acceptors. Okay, number 3 then, the final part is the replicas. Maybe adding more replicas will make the protocol faster. We'll have our clients as before. We'll have our proposers as before. We'll have our 3 acceptors as before. And now let's just draw a bunch of replicas. And again, we'll run the protocol. And we see, much like with adding more acceptors, this doesn't really help us much, and it just makes the protocol slower. I'm doing everything I was doing before, but now the leader has to send way more messages to all the replicas. So again, this doesn't help. It just makes the protocol slower. Much like with acceptors, typically the wisdom is not to use more than you need because they're not really doing anything extra. We're not getting more fault tolerance as long as we deploy enough. We already have our fault tolerance. Okay, any questions on that as to why naively multi-Paxos seems, at least on the surface, like it doesn't really scale? Okay, no questions, good. So now that I've explained that, I'll explain why none of that is actually true. So now we're going to tackle multi-Paxos, and I'm going to try to break up all of its bottlenecks and increase its throughput. And in order to do that, we first have to understand what are the throughput bottlenecks. So let's understand the biggest throughput bottleneck. I'll draw the protocol again. If I had $1 for every time I've drawn a little picture of multi-Paxos, that would be great. Okay, so we have our clients, we have our proposers, we have our acceptors, and we have our replicas. And I'll draw the protocol real quick. All right. So I will tell you that the leader is the throughput bottleneck. The leader is the bottleneck, and there's 2 reasons for that that are hopefully obvious just from the picture. The first reason number 1, is that everything goes through the leader. Every single command goes to the leader, and every single round of communication is orchestrated by the leader. So reason number one is that everything goes to the leader. And the second reason is that the leader is doing disproportionately more work per state machine command than all of the other components. To understand that, we can do a little back of the envelope calculation. This is a very rough, but in practice, it often turns out to correlate to the truth. What we're going to do is we can look at each of these components and say, how many messages, how many network messages is each component sending or receiving per state machine command? So if we look at the replicas, they all process either 1 or 2. The acceptors either do 2 or 0. So to explain this, for example, the acceptor receives 1 and sends 1. So I write 2. The top replica receives 1, it doesn't send any, that's 1. The bottom replica receives 1, sends 1, so I write 2. But the leader processes 7. So it's doing more stuff per command than every other component, and it's touching every single command, which means that that leader becomes the throughput bottleneck. So reason 2 is that the leader does more. So if we want to increase the throughput of multi-Paxos, then we're going to have to break this throughput bottleneck of the leader. Oh, Adam, did you have a question?
Yeah. So when do we want to talk about sharding? Because obviously, if we're sharded, a replica get overloaded, but you have multiple proposers coming from different, different data sets.
Yeah, great question. Sharding is actually one of the things we don't talk about too much in the thesis at all.
Okay, great.
I'm happy to talk about it more later, and we'll do some things which are very shard-like, and there are advantages and disadvantages to sharding. But for now, I'll leave it to later. But thanks for bringing that up. It's a very relevant, very pertinent topic. All right, so I want to bust this bottleneck. I want to break it up, and to do that, we're going to make the following observation. We're going to observe that the leader has 2 main responsibilities. Responsibility 1 is sequencing. And that is the fact that when the leader receives a message, a command, it puts the command in the log, and it makes sure that all of these commands are nicely getting ordered in the log. If we didn't have that, it would be a lot more difficult to sort of get this nice linear order of commands that we need. And the second responsibility is all this other stuff, which I'm going to call communication. So it orchestrates pretty much the entire flow of the protocol with every other component. And what we're going to do is we're going to say that these 2 responsibilities, which have historically fallen on the leader, they don't both have to fall on the leader. So we're going to have a 2-pronged approach. First, we're going to decouple. I'm going to decouple these 2 responsibilities. And let me show you how we're going to do that. So I'll draw the protocol again. I'll have clients. I'll have my proposers. I'll have my acceptors. And I'll have my replicas. And now what I'm going to do is, this is going to be very straightforward. I'm just going to introduce a new set of nodes that I call proxy leaders. And let me draw maybe 5 of them. Oh, and let me draw the crown. And the protocol is going to run like this. The client will send their commands to the leader as usual. The leader, as before, will sequence the commands. And now the leader, instead of performing a bunch of communication, is just going to forward its message to the proxy leader, any of the proxy leaders. So let's say it chooses this middle one. And this choice is random. It's arbitrary. Then the proxy leader is going to pick up where the leader left off and perform the communication. It's that simple. There's really nothing super fancy about this. Just introduce new nodes and have the proxy leaders perform the communication. So essentially what we've done is we've split up the 2 responsibilities. The leader is now responsible solely for responsibility 1, which was sequencing, and the proxy leaders are responsible for this other responsibility of communicating with all the other nodes. So what does this get us? Well, let's do that back in the envelope calculation again and see how many messages each node touches per command. The replicas are the same. It's either 1 or 2. The acceptors are the same. It's either 2 or 0. But now the leader only touches 2. So before it was 7, now it's 2. And intuitively, and also we can show in practice, that has a huge impact on the performance. The leader used to be sort of doing everything, and now it's doing as little as it can do. It just receives a single command and sends out something. But you might be saying, well, hold on though, the proxy leaders still have to touch 7. Have you really eliminated the bottleneck, or have you kind of just moved it to the proxy leaders? The answer is that we've eliminated it, and that's because we can do bullet point item number 2, which is scale. I told you earlier that adding more proposers didn't do anything, but now adding more proxy leaders does do something. Proxy leaders are completely, embarrassingly parallel. They scale completely. They don't talk to each other, and adding more of them decreases the load. And that's because the leader will load balance requests across the proxy leaders. So let's say another guy comes up, he says Y, the leader can choose a different proxy leader, something like this. Which means that if the proxy leaders are ever the throughput bottleneck, I'll just add more of them. And then eventually, with enough, they won't be. So this two-pronged approach, decoupling and scaling, that's what we call compartmentalization. I mean, neither decoupling nor scaling is novel. I mean, it's not, nothing here is sort of like rocket science. It's not really mind-boggling. It's just a very simple, straightforward technique of identifying bottlenecks, decoupling the components into smaller components, and then scaling up the components that scale. So I'm going to go and show you now how to use compartmentalization to compartmentalize the acceptors and replicas. But before I do that, are there any questions on this so far? Either compartmentalization or what we've done specifically with the proxy leaders?
Michael, do you want to say something about why you're not worried about latency adding the hop? Why you're trading a little tiny bit of latency, and I'm sure you're not concerned, but for the people who haven't read the papers, like why aren't we worried about that?
Yeah, great question, Peter. I'm super happy you brought that up. So I think there's actually a kind of a deep answer here, which I have in like the sort of lessons learned in the thesis. Stonebreaker wrote that one famous paper, like, I forget even what it's called, like Through the Looking Glass or something. No, one size doesn't fit all. Pretty much arguing that you shouldn't try to have one database that does everything. And if you look at Paxos papers today, you often find that the papers are like, okay, here's a new protocol that has super low throughput, or sorry, super low latency and super high throughput that works in the local area and the wide area, and it does everything. And through the research, we found that I don't think that's necessarily the wisest thing to do. And here's why. If you're deploying a Paxos protocol in a like a data center, counting the number of delays between when a client sends a command and here's a response, typically the literature is like obsessed with this. Like they will introduce like 15 pages of complexity to shave off one trip some of the time if the conditions are just right. And in a data center, through our experience, it honestly doesn't really affect latency that much at all. So we think that in those situations, the complexity added of all this complicated stuff is not worth it. And you shouldn't obsess over the number of arrows that you're drawing in the protocol. Whereas if you're in a wide area network where the delays now are really significant, then these more sophisticated protocols, which are shaving off the arrows, start to become important. So that's a long answer, but the short of it is sort of this is assuming a data center kind of deployment. We're really focusing on the throughput, and the latency maybe will go up slightly, but it's pretty insignificant.
It's a great answer. Thank you.
Can I ask a question?
Yeah, please.
What do you do if some of the initial client requests actually conflict? Like like instead of, say, I guess in your picture, the green request is touching X and the key X, and the other way around. Blue is touching X and green is touching Y.
Yeah.
If both of them need to touch X, how would you know, like from the leader, that everything downstream of it is finished? Do you need to send everything that touches the same key to the same proxy leader, or is that taken care of, in the like automatically by the downstream activity?
Yeah, good question. So ultimately, every command is getting put in some log entry. Every single command is going to get assigned a specific spot in the log, and the replicas will sort of be piecing together their log command by command, and they'll be executing the command in log order. As long as you do that, it doesn't really matter if the commands are chosen out of order. It doesn't matter if the replicas receive the commands out of order. It doesn't really matter how the commands conflict. Because at the end of the day, all the replicas are going to be sure, always execute log entry 0, then log entry 1, then log entry 2. And as long as we do that and everybody's always executing the same commands in the same order, we'll never diverge. Does that make sense? Oh, yeah. Go ahead, Joe.
Maybe you could help us by telling us which items in this picture are stateful.
Ah, yes. So the replicas, the leader has a little log. The replicas are also maintaining their own little log. The acceptors also have some state, which is a little more complicated. And the proxy leaders are pretty much completely stateless. I could shoot a proxy leader and it's totally fine. If I send something to a proxy leader and that proxy leader dies, it's whatever. I'll sort of resend it. It's not a big deal. In fact, you can know it's not a big deal because in the original Paxos, I could already send a message and it could just get dropped. Sending to a proxy leader and it failing is no different than just sending it normally and having it dropped. So the proxy leaders are pretty much stateless. They have some temporary state, but it's like soft state, I guess you could say.
Okay. All right. So the I guess it's when the leader, actually tags something, like this is the 0th command, this is the 1st command, and the replicas know, the order, like the actual order the leader gave them when they get them.
Yeah, there are some more complex details about precisely what is the moment when I know for sure a command is put in a slot and it'll never change. And that involves the acceptors and voting and stuff like that. That's sort of the details of the protocol. But at a high level, yes, pretty much the order in which they're getting put in by the leader, ultimately the replicas will respect that. And that's what makes sure they don't diverge.
Okay, that makes sense. Thanks.
Okay, cool. Anything else?
Well, I wanted to point out, like, regarding the comment that you can just shoot a proxy leader and be okay.
Mm-hmm.
Like, there is the very niche scenario if you broadcast to proposers, so then you have F+1 guarantee, then originally you would have been guaranteed that whatever you sent would be committed at some future time. But given proxy leaders, you might not, right?
Yeah, that's a good point, David. Yeah, so there's definitely some liveness things, I think, which will vary based on how you tweak things for sure. And that's a whole can of worms that I'm not going to get into. Liveness is safety was good enough for my thesis, and I'll leave liveness to people like David. Cool. Anything else? All right, I'll keep going. Hopefully I have enough time for the teasers and stuff. Okay, so that was compartmentalizing the leader. Now let's compartmentalize the acceptors. But first, let me motivate why I'm even doing that. So we had some protocol. I had some obvious bottleneck, the leader. Everybody knows the leader is a bottleneck. That's like every paper picks on the leader, like bullies the leader. And we tried to eliminate the leader as a bottleneck, and we either did that or at least we alleviated it. And now the question is, okay, what's the next bottleneck? That is a little bit more challenging to answer because it depends on a lot of factors, but it's not uncommon for the acceptors to be a bottleneck. Maybe they are in your deployment, maybe they're not, but it's not some super obscure thing. So can we then compartmentalize the acceptors and eliminate them as a potential bottleneck? Yes, we can. We're going to compartmentalize them. So let's compartmentalize the acceptors. Now there's sort of two things going on with this. I want to increase the number of acceptors, and there's sort of two challenges. The first is what I told you near the beginning of the talk, which was adding more acceptors places more load on the leader, which just slows down the protocol. That used to be true, but it's not anymore. If I had more acceptors, I place more load on the proxy leaders, but the proxy leaders scale. So that's not a big deal anymore. Before I was placing load on the leader and the leader doesn't scale, that was a big deal. Now it's not. So I can add more. But there's a second issue, which is still preventing us from doing this. And that is the fact that increasing the number of acceptors has diminishing returns on decreasing them as a bottleneck. Why is that? Well, let's say we have 3 acceptors. The leader has to talk to a majority of them, which is 2 out of the 3 nodes. Which means that over time, if I average over all the state machines, all the state machine commands, so leader gets 1 command, it'll send it to a randomly chosen set of 2, the next command to another set of 2, the next command to another set of 2. Over time, on average, every acceptor is going to receive 2/3 of all the commands. If I start increasing the number of acceptors, let's say 5 acceptors, I'm going to talk to 3/5, which is a little bit better than 2/3, but not by too much. If I go to 7, 1, 2, 3, 4, 5, 6, 7, I'll talk to 4/7, which is a little bit better than 3/5, but not by much. And if I draw a little graph with number of acceptors on the x-axis and the load on the y-axis, we'll start off at 2/3 if I have 3 acceptors, but I'll be asymptotically lower bounded by a half. You can give me 1 trillion acceptors, and still every acceptor is going to process roughly half of the commands. So adding more reduces their load, but only to a point, and that limit is not even that far off from like 3, 2/3 and a half is not that far off. So this is sort of the other problem with just naively adding more acceptors. And this is one of the reasons also why people think adding more acceptors doesn't help much. Well, we can scale up the number of acceptors, and we can do it in a relatively simple way. So first, we're going to do another decoupling. And what we're going to decouple is the acceptors across log entries. And what do I mean by that? Well, in normal Paxos, we assume a fixed set of acceptors, and we use those acceptors for every single log entry. But that's not necessary. We need to make sure that every log entry has a fixed set of acceptors, but we can use different acceptors for every log entry. If I wanted to, I could have a complete, it's like Oprah, you get an acceptor group, you get an acceptor group, you get an acceptor group. Every single log entry, if it wanted, could have its own set of machines. We're not going to do something quite that extreme. Instead, what we're going to do is we're going to have different groups of acceptors. So let's say I have 3 groups. I'll call this group A, I'll call this group B, and I'll call this group C. And then what we're going to do is we're going to partition the log amongst these different groups. So the first log entry will go to A, the second will go to B, third will go to C, then back to A, and so on. You get the point. So what is the protocol going to look like now? So we're going to have our clients, we're going to have our proposers, we're going to have our leader, we're going to have our proxy leaders, we're going to have our replicas, and now we're going to have our multiple groups of acceptors. And the protocol will go like this. The client will send the command to the leader as usual. The leader will put it in the log as usual. The leader will send to a proxy leader as usual. And now the proxy leader has to say, okay, this command X is in the first log entry, and the first log entry corresponds to the first acceptor group, so I'll communicate with them. So it'll talk to the first acceptor group and let the replicas know. And then let's say some other client suggests Y, it'll put Y in the second log entry, it'll send it to some other proxy leader, and the proxy leader says, okay, Y is in the second log entry. Oops, I did the wrong color. The second log entry should be blue, this second group. So it'll talk to the second group. Oops, you get the point. And one of the replicas will reply. So we're just sending to a different group for every different log entry. That was point 1. What did I say? Decouple acceptors across log entries. And point 2 is I can scale up the number of acceptor groups. If the acceptors are ever a bottleneck, a throughput bottleneck, I'll just add more of them, more groups, and eventually they won't be.
This speaks, I guess, to Adam's question about sharding from before, but internally to the protocol, yeah? Or sharding the log, essentially.
Yeah, for sure. I definitely think that it's like, this gives a lot of the benefits of sharding, performance benefits, without some of the disadvantages of we still, at the end of the day, have a single unified log.
Yeah, I guess that's a great point, which is we're not actually asking anyone to shard any of the data involved in the system. It's all just the internals that we're sharding. It's the mechanism.
Mm-hmm. Yep. Any other questions? Adam?
So I think if I understand what you're saying is that basically these groups, these acceptor groups, are handling essentially the failure of the replicas, but that's separate from the ordering of the log, and that's why this works, because they don't really have to be unified. So you really it's really the acceptor groups are completely independent of each other, is what you're saying.
Yeah, exactly. Another way to say that is the fact that we have a log is not fundamental. The acceptors don't really even care about a log. They just care about, here's some command in some thing called entry 2, and I just have to reach consensus on it. They don't care what comes before or after it. They have no notion of a log.
Yeah, that makes sense. Thanks.
Okay. So next I would tell you how to compartmentalize replicas, but since we're running a little low on time, I think I'm going to skip it and go to the next part. But that's the simplest part. You just add more of them. That's not super exciting. Okay, but let's skip ahead then. And let me get to part 2, which is the teasers. Or maybe let me spend at least 30 seconds kind of summarizing before I move on. Compartmentalization says, look, There's all these super fancy Paxos protocols out there that try to get high throughput. They're really complicated. But look, here's this one simple trick. You just decouple and you scale stuff. It's not super flashy. It's not super exciting, but it's really simple and it's really effective. And if you want to know more, I recommend checking out the paper. There's other compartmentalizations we talk about too, batching and stuff like that. Okay, but the teasers. So I want to spend some time talking about some of the other research that I've done, at least at a very high level, so that if you're interested, if something catches your interest, you can go read the papers. So first up, leaderless reads. Do I have time for this? I think I do. Okay, leaderless reads. All right, let me draw a little cartoon. There's not, I wouldn't call this a graph. Call this more like a picture. So we have number of machines on the x-axis, and we have throughput on the y-axis. And let's look at different protocols. First up, Paxos. It's a horizontal line because it doesn't scale. And by Paxos, I mean the naive version, not the compartmentalized version. We already talked about this. Naively adding more machines doesn't help. It only hurts. So if you get more machines, just don't use them. Compartmentalized Paxos does scale, but only to a point. So this scales to a point. I showed you how it scales and it busts bottlenecks, but ultimately there will still be some bottleneck, either the leader or the replicas, because still everything is going to the leader and still every replica receives every command. So at a certain point, we'll sort of peak out. And then you have some weakly consistent systems like Dynamo or Cassandra or Mongo or something like that, which have super nice scalability. They sacrifice consistency, but in return, they have this really nice linear scalability. And wouldn't it be great if we could have a protocol, a Paxos protocol, that looked something like the weakly consistent system that scaled linearly almost forever? The answer is, yeah, we can, with an asterisk. We kind of can. And the main idea is that we're going to take advantage of reads. So what does that mean? Well, let me draw the picture again real quick of the protocol. So we have our clients, we have our proposers, we have our proxy leaders, we have our acceptor groups, and we have our replicas. And a normal command looks like this. We always go through the leader and we go to all of the replicas. What we're going to do is we're going to say, if we have a read, and by read, I just mean some state machine command, which doesn't actually change the state of the state machine, for example, like a read, reading a key or something, then we can bypass both these bottlenecks. We don't have to talk to the leader and we don't have to send to every replica. I won't have time to explain how this works, but what happens is the client ends up being able to talk to just one acceptor group, hear responses, and then send to any of the replicas and get back a response. So we don't talk to the leader at all, and we only talk to one replica, not all of them. Because of this, if we have a read-heavy workload, our throughput begins to scale almost linearly. We can just keep adding more replicas and more acceptor groups. There's obviously some nuances. It's not quite, it doesn't always perfectly work like that, and it depends on reads and stuff. But if you're interested in that or that sounds cool, I recommend checking out the paper. Or the thesis is also in the thesis. Okay. I want to leave time at the end. So let me just say what the other work is about, and then let me get to the acknowledgements. So I also worked on something called bipartisan Paxos. Imagine, you know, we have these like logs, right? Everything's about the log. We have a log and we put all the commands in the log. What if we said, we don't want logs, we want graphs? Okay, that's a whole family of protocols called generalized consensus protocols. Instead of logs are so old, we're going to be hip and new, we're going to have graphs. There's a whole family of those protocols, and they are super complicated, really complicated. People think Paxos is complicated. These protocols are truly complicated. And we use compartmentalization to show not only that we can make things faster, but we can make things simpler. We take these complicated protocols, we decouple them into their sort of smallest components, understand each component in isolation, and then sew the components back together in a clever way to get back some of the performance benefits. And I think personally that it's the work we did is sort of the clearest and most sort of beginner-friendly tutorial on this entire family of protocols. And I think it brings a lot of clarity to the space. Whereas previously, I think a lot of people didn't really even understand what was going on. There's also something called matchmaker Paxos. The idea there is that when protocols run, eventually machines fail, and we have to replace those machines with new machines. That is similar to changing the tire on your car while you're still driving. It's very challenging. And it's very subtle and it's easy to get wrong. For example, Raft, which is another popular protocol, they had a protocol, a reconfiguration protocol that they learned very late in development was wrong, it was broken. They fixed that, and then they made a much simpler protocol, which they later found was broken. So these protocols are extremely hard to get right. And we developed one, which I think is simple, it's fully proven, blah, 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 blah. Okay, anyway, you guys can check out the paper. That I'll leave you to do on your own. But let's get to the acknowledgements, and then if I have time, I think I will for questions. This, I think, is the most important part of the thesis. So yeah, I've had the amazing opportunity to work with so many people over the years, and nothing I've done would have been possible without all these people. So I just want to take the time to say a huge thank you. So we'll start at the top with Joe, obviously my advisor. Joe, you were one of the biggest reasons that I came to Berkeley, and I'm so happy that I did. Working with you has been an amazing privilege. You are so smart. You are so supportive. You're so friendly. You've always had my back. You've always put your full faith and confidence in me. You've always looked out for me. And everything you've done for me, I sincerely thank you, and I really appreciate it. Jan, I've had the privilege of working with Jan for the majority of my PhD. Jan, you are so experienced and you have so much wisdom every time we talk. I feel like I learn something very insightful, whether it be talking about how to please reviewers or how to run a successful startup, career advice, life advice. I always really cherish the opportunities we have to chat. And I always feel like I leave the conversation having learned something. So I really benefited from that. Natasha, these first 4 people are all my committee. Natasha, I feel like our paths just quite didn't align as nicely as I would have liked. We were both at Cornell, but not the same years. We're both at Berkeley for 1 year, but during a quarantine. But even this 1 year in quarantine, the opportunity to work with you on the work with David and Kaushik has been amazing. You are so friendly. You make me happy about sort of the future of academics and how people can be so smart and so kind and so giving to others. So I hope we cross paths more in the future. It's been a privilege to work with you. Barna, who's been on both my committees, I appreciate all the time you've spent reviewing my stuff, looking over things, attending all my talks, and I always appreciate all the feedback and insight you have on all the work. So I appreciate that. Next, we have Heidi. So Heidi, I don't think Heidi's here. I think in the UK, it's probably, actually, I don't know what time it is, but I don't think Heidi's here. If you are, speak up, but I don't think so. Heidi, in my opinion, is the world's leading expert on consensus. She's a professor at Cambridge. She is an unstoppable force in the field. And the majority of this work would not have been possible without her guiding us in the directions that she did. Yeah, I can't understate how important her contributions have been to the research. And she's actually, if you Google Paxos on YouTube, she'll be like one of the top results. That's how legit she is. And yeah, I think that's pretty cool. Next, we have the trio of Alexei, Murat, and Eddie. That's these 3. Alexei, I know, is here, I think. Yep. So these folks were originally at Buffalo, and our collaboration started as just a simple email, and then it grew into something so much more. Compartmentalized Paxos could not exist without the research that these 3 had already done. The leaderless reads things, which I talked about, we pretty much stole that, but we're collaborators, so I guess it's not stealing. And Pig Paxos is very similar to our work, and we took a lot of inspiration from that. And Alexei in particular, we also had the opportunity to work on Coracle, which is another project. We've gone very close. I attended the reading groups every week. Alexei, you are also, I would say, one of the world's leading experts on consensus, also extremely friendly, and I've always enjoyed the opportunity to work together. Next, we have this gang from the University of Washington, Irene, Dan, Adriana, Naveen, and Jalene. I had the opportunity to work with some UW folks on a couple of projects. They welcomed me into their lab. I would sort of Skype into the meetings, even though they were all in person. I learned a ton from them. And Adriana in particular, we went on to collaborate on pretty much all the projects. She was a tremendous mentor, always somebody I could turn to, probably the most optimistic and positive person I've ever met. Even in like our harshest rejections, she would literally, you couldn't even tell. She was just like unfailingly optimistic and positive. Faisal, we collaborated on Matchmaker Paxos. This was another collaboration that started off just as an email, but he fostered it into something so much more. And the whole Matchmaker Paxos paper was super exciting. And I think that whole process was fun. Peter, who is in the building, you are my academic older brother and a huge influence on me in the earlier part of my PhD. I still remember we were at SOC 2018, I think, together. And I was super nervous for my first ever talk in grad school. And I think we were hanging out in your hotel room, and you were listening to my talk, giving me pointers last minute, telling me everything was going to be okay. You went for walks with me, giving me advice. So you've taught me how to conduct research, how to be passionate about things, and just how to be an overall sort of good person in the space. So I appreciate all your mentorship and friendship throughout the years. And finally, last but definitely not least, my partner in crime and my fiance Ava, who's also here. I mean, there's nothing to say. I mean, literally nothing would have been possible without your support every single day for the last 5 years. Everything you do for me, I appreciate so much, and I love you so much. And I'm happy we could go through this PhD journey together. So with that, sorry, I only left 2 minutes, but a huge thank you to everybody. And if there's any comments or questions, I'd love to hear them.
I'm just going to say out loud to everybody something I've been saying to you for a long time, which is your presentations are so brilliant on top of your work being so brilliant. And to those of you who are at Google, you got to make sure that Michael continues to be teaching people while he's inventing things. It's such a rare skill to be able to get on an iPad like this and just freehand to talk. But he does it every week at our meetings. And there's no way you could have gotten through this dissertation, Michael, or this research thicket without that clarity. And to the extent you can keep sharing it with people, please do. Awesome talk.
Thanks, Joe.
Yeah, I want to share Joe's feelings. I was actually thinking about emailing you after your talk to get some advice. How to do this? This was awesome.
Oh, thanks. Yeah, I'm happy to talk about this kind of stuff.
I want to echo that too. I think the talk really rose to like reflect the importance of all the work you've done and to invite everybody in on it. It's just really great. And I've never seen an acknowledgement section like that either. It's, wow.
Thanks, Peter. Thank you.
You make your work seem simple, and given the complexity and the subtlety of what you did, it's a fantastic skill, truly.
Thank you, Natasha. I appreciate it.
So, Michael, I think it was really a pleasure to collaborate and, to witness your presentation. And I think that one thing I always admired, it was your persistence. And really you wanted to do this, and it's a hard problem, crowded space, but you went for it and you did it.
Thanks, John. Yeah, persistence and consistency. I guess that's been the theme.
Indeed.
Cool. Well, yeah, if no one else has anything, we're at time. So thanks again, everybody, for showing up. And yeah, thanks for everything.
Congratulations.
Right. Thanks.
Congratulations.
Thanks, everyone.
Great work.
Okay. Bye, everyone.